Good morning, everyone. I am Christian Wimmer from Oracle Labs, which is the research organization of Oracle. Today I want to talk about one compiler, and you will see in a few slides what I mean about that. First, of course, the usual disclaimer slide. I hope you like what I talk about, but it's not a product yet, which means don't buy Oracle stock just because of this talk. I want to start out with looking at our all-beloved Java Hotspot VM and more or less have a little bit of a stack snapshot when you run the Nashorn JavaScript engine and see what do we have on our stack. And I actually split it in two parts, so you see the stack has a left and a right half. The left one is more or less what I see as the physical stack layout, and the right half is what I see as the logical stack layout, so where actually the source of the code is coming from. And for this talk, I want to focus more on the physical side, just to say that up front. What do we have on the stack? We have stack frames in lots of different formats, because we have, of course, in red, native code, which is C++ code coming from the Java Hotspot VM, which is C code coming from the Java native interface. We have Java code executed on the bytecode interpreter, so we have a stack frame layout for bytecode interpreters. We have just-in-time compiled code, which on the Hotspot VM we have two just-in-time compilers, client compiler and server compiler. Fortunately, at least the stack frame layout for these two compilers is the same, so we have compiled code on the stack. And then when we look at what we're actually executing, native code is either things, as I said, from the Java Hotspot VM or from JNI code. And the bytecodes that we're executing in the interpreter or the client compiler is either bytecodes coming from the .java files, or it's dynamically generated bytecode coming from JavaScript code. So you see that's a very colorful picture. And if you look at what the VM has to do, it's pretty difficult. So if you want to run a garbage collection, then the VM has to find out all the root pointers that are on this stack. So we have to traverse our stack, and we have to do everything 3 times. So we have to look at the native code, we have to look at bytecode interpreter frames, we have to look at compiled frames. And it's not only for this GC root pointer stuff. I would say most things, if not everything, in the Java Hotspot VM exists 3 times. So you have stack frame layout, as I said, bytecode interpreter frames, close to the JVM language specification with, you have local variables, you have expression stack slots. Compiled code by the client and server compiler, you have spill slots that the compiler emits. And in the native code, you have whatever the C compiler is doing, you have no clue. The stack frame size for bytecode frames is variable. For compiled frames, it's fixed. And native code, again, we have no clue. If we want to do exception handling in Java, in the bytecode interpreter, first about root pointers, in the bytecode interpreter, we have to do some liveness analysis during garbage collection to find out which of our local variables are currently objects, which are non-objects. So we have to do some expensive computation during garbage collection. In the compiled code, the compiler gives us pointer maps, and in native code, we have explicit handles. And everyone who has worked in the Hotspot VM knows it's pretty difficult to really capture every Java object in a handle at the correct places. And if you make a mistake, then you will get crashes at random places after garbage collection because you haven't updated a root pointer. The same for exception handling. You have 3 different implementations. If you want to port the Hotspot VM to a new architecture, you have to port the bytecode interpreter, write assembly code, you have to write 2 JIT compiler backends, and you have to write the GCC backend for the C code. Debugging, again, you have Java debugging for the Java parts, you have native debugging for the C++ parts. So you have a lot of complexity. And the real question for us is, can we simplify that? And the way we want to simplify that is by saying, well, why do we need these 3 different execution environments? So why do we need everything 3 times? Why not just have one compiler and unify all of that and get a much simpler system? For those of you who have followed our Oracle Labs research, we have this project called Graal and Truffle in Oracle Labs. And I have to give you a few slides to set the context. Yes, it's also our usual advertising slide, so you can see, well, it's the commercial break here. But you also have to understand the basics so that you can follow then what I'm talking about later on. So what Truffle gives you is it's a language implementation framework where you just write an AST interpreter for every language you want to execute. So we have an implementation for JavaScript, for R, for Ruby, for LLVM bitcode. So you run all of that managed on the Java, on this Truffle layer written in Java. And the Graal is our just-in-time compiler. It automatically optimizes and compiles all these languages. And on the other side, we also have tools. So we have debugging for all of these languages. And the main takeaway point from this slide is that tools and just-in-time compilation are not at all related to the language implementation. You see there's no line between Graal and the languages, which means when you implement a new language, you have absolutely nothing to do with compilation. You get that for free. You have to do very little for tool support, and you get automatically, for example, a debugger for free. The whole stack is written in Java, so you can run it on the Java Hotspot VM. For Java 8, you have to download our build, which exposes the just-in-time compiler using the JVM CI API. Starting with Java 9, you can take a stock Hotspot VM, which will be a big simplification because all the hotspot changes are already in there. But what I want to talk about in this talk actually is Substrate VM, which is our reduced environment to run all these Truffle languages on a much simpler stack, and that's where we see our stack will look really better. If you're more interested in Graal and Truffle, there's actually a workshop later today where we can answer all questions. But if you want to dive deeper, we have in total about 6 hours of tutorial videos on YouTube that you can watch on all sorts of Graal and Truffle topics. The way Truffle optimizes it, you write an AST interpreter, but you write it in a self-specializing way, so you provide feedback in the AST interpreter in your tree nodes and say, well, I have an addition that I specialize to, well, that's an integer addition, and that's what you do as a language implementer. But then the compilation, which uses partial evaluation, is completely for free because that's done transparently by Graal. And also going back from the AST interpreter, from the compiled code to the AST interpreter, in case your speculation does not mirror it's not the complete truth, then that's also done by the infrastructure. And the 2 important things on this slide, why they are relevant for this talk, is that we have this compilation using partial evaluation. I'm going to talk a little bit about that. But I'm going to especially talk about this transfer back to the AST interpreter, also called de-optimization, and how we implement that on Substrate VM. But we are nearly at the end of the commercial break. Just what do you get if you run all this infrastructure just on the Hotspot VM? And that's actually a thing. You can go to our page on the Oracle Technical Network. You can download the whole thing. You can run all that yourself. So you can reproduce all the numbers at home if you want. For Java code, Graal gives you the same performance, more or less, as the Java Hotspot server compiler. For what we call more modern forms of Java bytecodes, like emitted by Scala, Graal already beats the server compiler by about 20%. For languages like Ruby and R that don't have a fully optimizing JIT infrastructure in the basic language, or for Ruby where you have JRuby, where you have this layered approach on the Hotspot VM, our Truffle approach really gives you big speedups in the order of 4 to 5x. Interesting native, if you run C code or Fortran code on top of the Truffle infrastructure on the Java Hotspot VM, you get about 85% of the performance already that you get when you have highly optimized static binaries coming from GCC or LLVM. And for JavaScript, of course, the comparison is with V8 is the bar is much higher, but we reach also more or less already the peak performance of highly optimized JavaScript runtimes. But unfortunately, just running the whole stack on the Java Hotspot VM doesn't really solve our big mess on the stack. The right side, the logical source of where the source code that we execute is coming from is a bit simpler, because at least with Truffle, what you have is everything that you execute, all the bytecodes are actually coming really from Java code. So you never have automatically generate bytecodes that are generated at runtime, like Nashorn is doing. But the left-hand side, our physical stack layout is still exactly the same as before. So there is no improvement on that side, because you still have your native code, you still have your bytecode interpreter frames, you still have the compiled frames, and, well, you have Graal compiled frames now, but they have the same stack frame layout as the client and the server compiler had before. So running on top of the Hotspot VM is, with Truffle is not really simplifying our life. So what we did with on the Substrate VM project is we want to run our Truffle and Graal stack on a much reduced system that we can really embed into other products. And by embedding, I mean not real small embedded systems, but I mean large server applications written in C, C++, and obviously Oracle has a large legacy code bases like the database, where we want to integrate in. But we want to embed our stuff that's written in Java. It's actually written in a subset of Java, because we simplify our life by saying, well, we don't need things like dynamic class loading or reflection. So we really focus on stuff that Truffle needs. Ahead of time compile all this Java code using Graal, and then we get a static executable, and we can debug, profile that with all the usual low-level tools like GDB or vTune or all of your native code profilers. And now suddenly we get a very simple picture when we look at our stack, because we only have code on the stack that's coming from one compiler, and in our case, that's the Graal compiler. Because our whole VM is written in Java and AOT compiled, all of the VM code, like even the garbage collector, is code compiled by Graal, and we know exactly what stack frame layout it has. Startup Java code, that's AOT compiled Java code. Things that were before native code of JNI, that's what we write in a low-level dialect of Java. I will talk about that a little later on. But it's also still Java code. Our JavaScript code first runs in the AST interpreter, and the AST interpreter is written in Java. So again, Java code is running. And hot Java code and hot JavaScript code, of course, that's then just-in-time compiled. And also Graal is the just-in-time compiler. So we really only have stack frames coming from one compiler and one layout. And also the logical source of the stack frames is the same, because everything is actually coming really from bytecodes that are somewhere lying around as .java files on your system. So there's nothing automatically generated, there's no automatically generated bytecode. You can really always go back to, oh, I have this machine instruction, and using all the all the metadata that we have for debugging, you can always pin down every machine instruction to really a line of Java code, which is really good for debugging and trying to find out what's going on. And if you want to optimize languages like JavaScript, what you really need is specialization, and that's what Truffle is giving you. But specialization always requires de-optimization. This is this transfer back to the AST interpreter. And since we want to run everything in this one compiler, one stack frame layout setting, We obviously cannot de-optimize like Hotspot is doing. We cannot de-optimize back to a bytecode interpreter. We have to de-optimize back to AOT compiled code, so we have to de-optimize to code that's also generated by the Graal compiler. And I will talk about that in more detail in a second. But a few more words on how Substrate VM is working. So what we are doing is we take all the Java bytecodes that we have, which is the JDK, which is our truffle language implementation, which is the Substrate VM runtime code. We do static points to analysis to find out what is reachable, and then we use Graal to ahead of time compile that, and you get a single executable. On Linux, you get the ELF binary, and that's then your JavaScript binary. The building blocks, our runtime system, all written in Java, sounds more like research than it actually is, because garbage collectors have been written in Java for decades now. So IBM started that with the JIKES RVM, Sun Labs, and then Oracle Labs had the Maxine VM, which had a garbage collector written in Java. So there's nothing really exciting about writing the whole runtime system in Java. So I'm not going to talk much about that. I'm only going to talk about the de-optimization system. Points to analysis, I have a few slides on that on the end, but probably I won't have time to really go into that because I want to spend a little bit more time than actually on the system Java part, which is our integration with C code, so that you get some details how we do that. Why does this one compiler approach work with Graal as the one compiler? That's because Graal is really designed for flexibility. And by flexibility, I mean it's really aggressively optimizing, but you can configure everything. It has this modular architecture where you can add phases, remove phases very easily, but also where the compiler and the VM is strictly separated. So you can take the core compiler, so you can take 95% of the whole project, which is VM independent, and just write a little bit of glue code to the VM, and then you can run Graal in a completely different setup, in a completely different VM. So you can run the same compiler on the Hotspot VM, you can run on the Substrate VM, you can use the same compiler to do ahead-of-time compilation and dynamic just-in-time compilation, and that all works nicely. And it also gives you really good peak performance because it's designed from the ground up for these speculative optimizations that you need for languages like JavaScript and all the other dynamic languages like Ruby and R. Let's talk about de-optimization a bit to get into some technical details here. De-optimization, has many names. Sometimes it's called an uncommon trap. Some people call it on-stack replacement. That's a term that I don't really like because Hotspot uses that term for when it switches from the interpreter to the compiled code, but in some literature also it's called on-stack replacement. We call it, I think, de-optimization pretty consistently. That's when you transfer from optimized machine code back to some sort of unoptimized code. And what it gives you is you can have much more aggressively optimized code and much shorter optimized code because you don't have to deal with all the corner cases. So the Hotspot has been doing that since the very beginning for things like, well, you can speculatively optimize virtual method calls, and if you later on load a new class that invalidates your inlining decision for a virtual method call, so the calls actually can no longer be devirtualized, then you just de-optimize and throw away the machine code. And for JavaScript, that's even used much more. It's in the interpreter, you profile, well, this local variable is always of type int, so I aggressively compile things as if it really is an int, but it's JavaScript, so at runtime, it can at any time be anything else. It can be a string, it can be an object, and in that case, you just throw away the code and you optimize, re-optimize again. So de-optimization is really the key part to enable speculative optimizations. And You cannot get good performance for dynamic programming languages without it. How is it done on a Java Hotspot VM? You have an optimized method on the stack here in green on the left-hand side. And usually you have inlined methods. You say, well, I have a root method f1 that I compiled, and I inlined two other methods, f2 and f3. And when you de-optimize, you actually, on the physical stack, you reconstruct three bytecode interpreter stack frames. And the layout of these bytecode interpreter stack frames is really given by the Java by Java language specification, because the interpreter is more or less following this model very closely. So it is really that on the bytecode interpreter frame, you have an area for all the local variables, for all the expression stack slots, and the compiler emits metadata to map from the optimized code back to this Java specification of local variables. So the compiler has metadata saying, if at this point I have to de-optimize, then local variable 0 has to be filled with this stack slot, and local variable 1 is dead, and local variable 2 has to be filled from this optimized stack slot, and then de-optimization takes that and builds an interpreter frame. And to make that work actually without an interpreter, we have to change our right-hand side here, because we don't want to de-optimize to an interpreter frame. We want to de-optimize to a compiled frame. But it turns out that it's actually not too difficult, because we can just compile these frames, these de-optimization entry points, with Graal2 as the compiler. And we compile it in a special mode, where we, you could say, disable a lot of optimizations. The one biggest optimization that we disable is method inlining, because obviously when you really want to reconstruct individual frames, it would be far too complicated to match up a method with an arbitrary number of inline frames with some other arbitrary number of inline frames. So you really say, well, you have, for every method you want to reconstruct on the frame, you have an ahead of time compiled Graal method for that. And when we do this special compilation for these de-opt entry points, we generate the same metadata that we also generate for the de-optimization source. So what we now have is, instead of matching compiled frames using this metadata directly to interpreter frames, we actually have a two-way matching, because both the source and the target now have a matching based on the Java language specification. And then you can do this matching. You can say, well, if I want to reconstruct my method f1 on the target stack, then I know, well, local variable 0 is actually should be in this stack slot. So how do I fill this stack slot? I say, well, I fill it with local variable 0, which in my original metadata comes from this stack slot. So instead of a one-way matching, you have a two-way matching, but it's not much difference. That's all what I just said. Let's look at a little bit of an example for that. I have a simple test case, a synthetic example, where we say, well, we have a Java method. It's named proxy needed, for reasons you will see immediately. And we assume we want to actually de-optimize here after this field store. Why do we want to de-optimize after the field store? The way Graal works is that every instruction that actually changes some memory state might be a de-optimization entry point. Because the rationale is that as long as you're executing code that has no side effect on the memory, you actually you don't really need to de-optimize exactly at a place in there. You can say, well, you can always de-optimize immediately after the last state changing instruction, and then just re-execute everything that you did in the optimized code. So you can reduce the number of de-optimization entry points that you have by saying, I don't have to de-optimize exactly to the point after I did an addition or after I did a multiplication, because you can easily redo that after de-optimization. So you can always de-optimize back to a point immediately after the last state change, because you cannot undo memory stores, you cannot undo arbitrary method calls without transactional memory. That would be too complicated, but you can easily undo things that only affect local variables. That's why when we actually do a really normal Graal compilation of this method, what we get is, that's a little snapshot of Graal.ir here on the bottom left side. You get control flow nodes. Well, you have a method start node, then you do a store field, and then you do a return, because these are the instructions that you really have to execute in control flow order. And you have things like the multiplication. These are instructions that you can freely reorder, so these are floating instructions that are not in the control flow. And Graal does the obvious thing. You have the same multiplication twice, so you have the parameter x, you multiply by 2, you do multiply by 2 again, so you get a global value numbering, and in the compiled code you only get one multiplication, and the output of the multiplication is both written to the field and returned. What you have in green in this Graal graph, these are the frame states for de-optimization. You say if you want to de-optimize to the beginning of the method, then you need to de-optimize to the method proxy needed at bytecode index 0, which is the beginning of the method. And when you de-optimize to this point, then you have to fill the first local variable actually with this parameter, because that's the method parameter is always, it's also the first local variable according to the Java specification. And if you are after this field store, then you cannot de-optimize to the beginning of the method again. You really have to de-optimize to the point after the field store, which is then bytecode index 6. But still, the first the state you have to reconstruct is you have to reconstruct the first local variable has to be filled with the parameter. So you have two different de-optimization points where you can de-optimize. So we have to support these two entry points in our de-opt entry code, and we do that really explicitly in Graal by saying we insert fixed control flow nodes saying, well, we have a de-opt entry point here, and we have another de-opt entry point here, and they both have their own frame state again. Saying if you de-opt to here, then yes, you have again bytecode index 0, and if you de-optimize to this frame state, then you de-optimize to bytecode index 6. So let's assume we de-opt to this bytecode index 6 at this point. What happens is to look up this de-opt entry point, the steps are you have optimized meshing code with a program counter. You look up the metadata to find this frame state. This frame state says, well, it's this method with bytecode index 6. You look up the de-opt entry point for this method, which would be this graph. You look in this graph for the matching frame state of a de-opt entry with bytecode index 6, which would be this point. And then you know, well, this is the point you have to de-optimize to. There's one little thing that we still have to account for is we have to make sure we don't optimize these de-opt entry points too much. Because now execution really continues in the middle of a method. So when we start executing at this point, actually the parts previously in the method here are not run again because, well, we are coming actually from this point. So we have to make sure that here we don't do any too aggressive optimizations, because we now have to really run this multiplication here again, because our Java level frame state only says that we have the parameter x available. So there's no way that during the optimization we can actually capture and store intermediate results like x times 2 that have not been stored in a local variable. So we have to make sure that we really re-execute that after de-optimization. And the way we achieve that is that after the de-opt entry, we just insert little proxy Graal nodes into the Graal graph, which make sure that the value numbering, which Graal normally does automatically, does not happen. So now Graal can just normally compile this method, but it knows that it can never remove the second multiplication because actually the input argument is different. And just by wrapping the input argument into a proxy placeholder node, we make sure that Graal does not do optimizations that we don't care about. So we don't have to reconfigure Graal to compile AOT, these deopt entry points. We just emit a little, a few extra nodes, and then everything falls in place automatically. Second thing I want to talk a little bit about is our low-level system Java parts. So when we write everything in Java, when you write the garbage collector in Java, you also have to make sure that you can really do raw memory accesses. Because, well, if you write the garbage collector, you cannot do that just by following Java rules. And we use the same infrastructure to integrate with C code. And when we have pre-existing Java code like the JDK that violates, you could say, our constraints because JDK uses reflection and dynamic class loading, then we just patch this Java code and say, well, we just substitute a few JDK methods. What is the system Java versus JNI? What's the difference? The difference is that with JNI, you write custom C code. So when you interface from Java to C, you have to write C code wrappers. So the C code knows about your Java types, and Java objects are also passed to the C code. And Java codes are passed to the C code, which means you have to wrap them in handles, and that makes things complicated because now the garbage collector has to correctly traverse these handles. In contrast with system Java, you write all this custom glue code in Java, and the Java code now knows about the C types. So there's no need ever to pass Java objects actually to C code, which means you don't have to deal with all the complicated handle stuff, because if you really have to call C code, and at some point you have, if you want to do a print line, then at some point you have to call into the OS kernel to really do the output. But that's a code where you already give out only native memory, and so the garbage collector does not need to deal with these frames. The only requirement for that is a low-level raw pointer type, or actually a machine word type. Currently, we fake that using an interface, but I'm really looking forward to value types in Java, because then we could just say, well, we have a value type for an unboxed machine word size, and things will look much nicer. But until we have that, we actually import and fake, you could say, C information using Java interfaces. So for example, if you say, well, you want to import the time spec C structure, which is used by time functions. So you have this C code for the structure. You have two structure fields for seconds and nanoseconds. And you import these structures and these fields to the Java side using an interface that's it's a words type interface, and it has two accessor methods. So it looks really nice on Java code, because now you can write low-level Java code like we have here in the bottom left corner that actually calls out to C code, but we can still argue it looks like Java code, and you get some sort of type safety. You get because at least you have to do explicit casts between structure types if you need to. But you don't get any memory safety because you can still, of course, access null pointers, raw memory as you want. But with this little snippet, we say, well, we have the time spec structure imported to Java. We want to get the size of it. We want to allocate memory on our stack frame so that we can pass the pointer out to a C function. The C function returns, and then we access the elements of the C structure and sum them up correctly and return them. So that's code that with JNI you would usually write in C, and we write it in Java. A few words on points 2 analysis. If you're interested, then talk to me or look at the slides later. We also use Graal as a static analysis framework. That's the the quick summary. Because Graal and the hosting hotspot VM, they already know how to pass bytecodes, how to load classes, so we don't want to implement all of that. So we use Graal also as the basis for static analysis. And I don't go into these details. A few results. Actually, I have a little JavaScript benchmark that we can talk about, but I think I want to show you instead one result really live. And that's what you really get is improved startup performance. So when you want to start up normally JavaScript VM written on top of the hotspot VM, you have to start up hotspot, which takes half a second. You have lots of memory that is allocated. Instead, what we are doing with Substrate VM is we are building a native executable. And I built a special executable that has a flag enabled to sum up all memory allocations so that we see at the end, well, how much memory do we really allocate? And I start up my JavaScript engine, and you see the prompt really comes immediately, so it takes only milliseconds to start up. And it really is JavaScript, so you can do something. And if I exit my JavaScript VM, prints out what we've allocated, but you see, well, we executed JavaScript code, we started up a full JavaScript VM, everything, and in total we allocated 90 kilobytes of memory. So that's really the same level that you would get if you start up V8 natively. Or it might be even already less than what you get with V8, because we can do a lot of, actually, a lot more during when we build the executable. So you see, well, we were running JavaScript, and I was only running Java code here. So everything that in this JavaScript engine, the whole runtime system is written in Java. But we still get the same performance, the same memory behavior as we get with native code. And with this little bit bigger benchmark, we just sum up numbers. And I have a couple of slides here where you see, well, if we run only very few iterations, then we do a startup benchmark where we see Substrate VM, this line, is actually starting up in more or less no time. So you get the same startup behavior as V8. At some point, then, of course, we start compiling. So on the long run, if you run really many iterations, you get the same peak performance that you get also when you run a Truffle on the hotspot VM. And for this benchmark, actually, the Graal compiler is doing a much better job than all the other JavaScript engines, because you see here, I have actually object allocation and object access in my loop. And Graal has a very aggressive escape analysis. So Graal can really reduce this loop to just summing up numbers, versus all the other JavaScript engines have to do memory accesses in every loop iteration. That's why the peak performance is so much better. Okay, in summary, Substrate VM uses a one compiler approach, which really simplifies the design, because we have one code to walk the stack, and it's really simple because we have only one kind of stack frame, we have one kind of exception handling, we have one compiler that we need to port to new architectures, we have we can look at our whole stack with one debugging tool like GDB and one profiling tool like vTune. We use Graal in many different configurations for all levels. So we compile Java code, we compile our low-level system Java code, we compile JavaScript code, we compile Ruby code, we compile R code, all with the same compiler. We compile the optimization entry points with Graal, and we use Graal for static points to analysis. And Graal really is flexible enough to support all of these use cases because of the clear compiler VM separation, where you can just plug in new VM backends, and because of the configuration of phases. All of that is, of course, not done by me alone. So we have a pretty big team at Oracle working on all levels of the Graal and Truffle stack. And we have lots of university collaborations, so a small army of master and PhD students helping us out too. With that, that's all that I had. So thanks for your attention, and I'm happy to take questions.